Alright gang, this is section 5.1. Definitely changing gears from 5.0. 5.0 was obviously about scatter plots and the lines of best fit that go along with those scatter plots. But here we're going to be talking about systems of equations. Okay? And this is just an intro to systems of equations, I suppose. And the first activity here is create an XY chart for both linear equations. Now, it's worth noting that an XY chart is just going to be a collection of what? Starts with an S. Solutions is the word I'm looking for. So we want to create an XY chart for both linear equations. So for this guy, if we just kind of go with the classic, I don't know, -2, -1, 0, 1, 2, and maybe the same thing for both, for the other one, I mean. Alright, so if I let x equal -2 and y equals whatever x is minus 2, and again, if x is -2, what's that going to make y? -2 minus 2 would be -4. If we let x equal -1 instead, y will now equal -1 minus 2, which is -3. If we let x equal 0, that's going to be -2. If we let x equal 1, that's going to be -1. And if we let x equal 2, y will equal 0. Over here, in the other equation, y is equal just to negative whatever x is. So if we let x equal -2, that's going to be -2, which is +2. If we let x equal -1, -1 will be +1. -0 is really still just 0. If we let x equal 1, then y would equal -1 and -2. So this is just like a list, and right now there's only 5 of them, but I mean theoretically we could come up with an endless number of more solutions. That was good grammar, right? So we could come up with as many solutions as we want for this equation as well as this equation. But I just want to emphasize as much as I can that -2 and -4 together as a pair of numbers, one number plugging in for the x and one number plugging in for the y, together these two numbers solve this equation. Same with -1 together with -3, together make one solution to this equation. Just like over here, -2 and +2 together plug into this equation to solve it. So for something to solve a linear equation like this, it takes two numbers, one number for the x and one number for the y. It's not like back in the good old days where you don't need to write this down necessarily, but all this took, right, was one number. So a solution to this equation would just be a single number, and it's in this case 10. 10 plugs in to here to make this equation true and solve the equation. So just take one number, and there's only one solution to this guy. But for these linear equations, takes a pair. Anyway, so we've created at least a small XY chart for both linear equations. And the question is, what point do they share? Well, can we tell, as luck would have it here, if you compare both tables contain the solution, the point, okay, 1 comma negative 1. Here's another way. Graph both lines on the coordinate plane. Okay, that's easy enough. So in order to graph these linear equations, it's nice when they are in that format, that form, y equals mx plus b. So here, it looks like my m would equal 1. So that's slope. And so more specifically, 1 over 1. So we'd have a rise of 1 and a run of 1, both positive. Positive 1 rise, positive 1 run. And the b would equal negative 2. So we begin with b, the y-intercept, and then we move with m. So my rise of 1, run of 1. So there's my slope, up 1 over 1, up 1 over 1. And, you should always plot as many exact points as possible and make your line as straight as possible, or as accurate as possible, I guess, passing through all the correct points. Does this one also fall under y equals mx plus b form? It does. M, the value in front of x, which is going to be our slope, would actually be negative 1, which as a full fraction for rise over run is negative 1 over positive 1. And there's no plus anything really, which means it's actually technically plus 0. So to graph this line, my y-intercept would be 0, but then my slope would be down 1 over 1. Down 1 over 1, down 1 over 1, even in the reverse direction. And so as you can see, I guess, right away, hopefully, is that when you graph these two lines, it's really, really, really easy to see what point they both have, right? Remember this question a moment ago? What point do they share? Well, looking at a graph, it's blatantly obvious to see what point they share. It's where the lines are going to intersect each other. So as you can see, it's what were the coordinates of this point? 1 comma negative 1. And so before we jump into some more repetition of examples, I just want to point out as clear as I possibly can what we've just done, okay? So this entire section was called Intro to Systems of Equations, right? And that's not equation, that's equations, as in plural, more than one equation, So the whole idea is going to be solving these things, right? Again, if I said solve this, right, you would just get x by itself and have the one and only solution. If I said solve an equation like this, that's kind of a weird request because there's an infinite number of solutions to an equation like this. They're all pairs of numbers, but there's still an infinite number of them. But if I said solve this system. And that's really what the word system means. Two or more equations. So when the task is to solve this system of this equation and this equation at the same time, all it really means is probably what you would expect. You are looking for any pair of numbers that not only solves this equation, but it also solves this equation at the same time. And graphing both lines to see what solution / point they share, that would do the trick. So that's going to be a big strategy for us. So moving on to this example, if I said, let's solve this system, what we're looking for is any xy pair that solves both, and we can graph these two lines in order to figure that out. So m equals -2, which is really like that, -2/1. b equals -4. So we begin with b, -1, -2, -4, and then we go down 2/1, down 2/1, down 2/1, even in the reverse direction, to make sure my line is passing through all the correct points. And we're going to find where these two lines meet, which is essentially going to solve this system of two equations. So what's m going to be here? Y equals mx plus b. It's in that form. So m is what's in front of x, which is really just a 1, and so 1/1. My y-intercept looks like +8. 1, 2, 3, 4, 5, 6, 7, 8. Up 1/1, up 1/1, even in the reverse direction. And we just figured out, really, already, where these two lines meet, and therefore what would be a solution to both equations at the same time, right here at -1, 2, 3, 4, -4, comma, looks like -4, comma 4. So right here, this -4, comma 4, that would be what would solve the entire system, because, you know, -4, comma 4 would plug in to solve this equation, and it would also plug in to this equation to solve it. Next example, I would recommend pausing the video if you missed class today or whatever, whenever, and see if you can solve this on your own. All right, here I go. So solving the first equation, where m would be 5/1 as my slope, and my y-intercept would be 9. Sorry, -9. That's what -9. So there's my y-intercept, and my slope says a rise of 5, a run of 1. So 1, 2, 3, 4, 5/1. 1, 2, 3, 4, 5/1. 1, 2, 3, 4, 5/1. And the other one would have a slope of 2/1 and a y-intercept of -6. So 1, 2, 3, 4, 5, 6. And, oh, already got it. Why am I still plotting points? I already know the answer like 5 seconds ago. So right here, that would be the point that they share, and therefore the solution that both equations share at 1, 1, 2, 3, -4. So that's the point of intersection, therefore the answer, the solution to the system of equations, right? Now think of two parallel lines. Do they ever meet? Once you think you got an answer to that, think of one line exactly on top of the other. Do they ever meet? Well, let's investigate, I guess, by graphing these two lines. So this one would have a y-intercept at -9 and a slope of up 2/1. And the other equation would have a y-intercept of 5 and also a slope of 2/1. So these two lines are parallel. What makes them parallel more than anything is that they have the same exact slope as each other. So it means they're never, ever, ever going to cross. They're always going to be like the same distance apart because of that same slope. But again, they're never going to cross. So they never meet, which means, even though this equation in red, okay, has an infinite number of solutions, like 0, -9, or 1, -7, or 2, -5, or any point, whether nice coordinates or nasty, ugly decimal coordinates, this equation has an infinite number of solutions that live on this line. This equation has its own infinite number of solutions that all live on this blue line, but they don't have any solutions in common because these two lines don't share any points. Okay? So the answer here is no. And as far as what would be the solution to the system of these two equations, quite frankly, since they don't share any solutions in common, the system has no solution whatsoever. And that's how that goes. That's how that cookie crumbles. Well, what about this system of two equations where it's the exact same two equations, where the y-intercept is 4 and the slope is 3. Oh yeah, I'm going through all this. Going through the motions, even though I think we all can tell what's about to happen. If the exact same equation with the exact same b and m values, which makes it, spoiler alert, the exact same line. So do these two lines ever meet? Do they share any points in common? Well, they share every point they have in common. So they intersect everywhere, right? They share all of these points in common. Every point that's on each line they share in common. And so as far as like what would be the solution to the system, like what points solve both of them, well, there's an infinite number of them, so I can't exactly list them all. Like 0, 4, or 2, 10, right? Or -2, -2. There's an infinite number of them. I can't list them, so I'm just going to write there's an infinite solutions. Okay? And that does it for the intro into solving systems of equations. The summary on that is that, if you were to graph both lines, you'll get a pretty good picture of what points and solutions that both equations share, and therefore, like, what would be the solution or solutions to the system.